when we think about linear models in the modern day, we think about the situation where we have only factor input and where we have only continuous input and where we have mixture of factor and continuous inputs all under the same footing. So we have the so-called ANOVA model, ANOVA model and regression model. But when statisticians were first encountering this idea of linear models, they were almost exclusively working with the situation where we have only factor inputs. So regression was initially considered to be a separate field of study. So they were working with something which are simpler in setup than what we tackle in terms of linear models nowadays. Even then, to come up with such an algebraic identity was not an easy task. When we have only one factor input, then yes, they could come up with this simple algebraic identity, and that sort of tempted them to look for similar such identities in a more general setup. But they soon figured out that if we have multiple factor inputs, then obtaining such an identity was a formidable task. Now for this, they figured out that if we have a situation like this, where we have got say 3 factor inputs that have color coded as red, purple and blue, then if you want to get such an identity, that is not always possible. And the condition under which that is possible was an interesting one and could be expressed in linear algebraic terms. So you look at this design matrix. So this is our design matrix. Now every time you have one input, that contributes a number of columns to your design matrix. Like if you have only one factor input, in that case you have some alpha columns. If you have 2 factor inputs and the corresponding parameters are alpha 1, alpha 2, alpha 3 and beta 1, beta 2, in that case you will have 3 alpha columns and 2 beta columns, like that. So every input contributes some columns to the matrix, and you also have typically the intercept column. The very first column, the something that I have shown in gray, that is the intercept column. So that's a single column, and then there are multiple columns. So I have shown 3 different inputs and each contributes its own batch of columns. And they soon figured out that the condition under which such a splitting is possible is when, loosely speaking, the red column, that space spanned by the red columns is orthogonal to the space spanned by the purple columns, which is orthogonal to the space spanned by the blue columns. Now, I said loosely speaking because I have the intercept term. So basically the idea is, if you take out the effect of that intercept from all these 3 sets of columns, then whatever is left out, they are actually orthogonal. So if you can't visualize it, think of it in this way. Suppose in R3 I have the xy plane and the xz plane. Now intuitively you will say that these are perpendicular to each other, but that does not mean that the xz space is orthogonal to the xy space, because there is something common. But what you can say is that if you take out the common part, which is the x-axis, then whatever is left out, so in the xy plane, whatever is left out, not as a set-wise thing, but in the sense of a vector space, so what is left out is the direction of the y-axis. So the xy plane is actually sum of the x-axis and the y-axis, sum in vector sum sense. Similarly, the xz plane is sum of the x direction and the z direction. So if you take out the common x direction, you are left with the y direction and z direction, and they are really mutually orthogonal. So our intuitive idea that xy plane and xz plane are mutually orthogonal is not correct. It is correct once you take out that common thing, that common x thing. Similarly here, the red set, that has a span, the purple part has a span, the blue part has a span. I am saying that they do have something common, they're allowed to have something common, and that is the intercept thing. Once you take that out, whatever is left, they are mutually orthogonal. If this condition is satisfied, which in general may not be satisfied, but if this condition is satisfied, then it is possible to split up the total variation that you see in the output in terms of total variation, in terms of component variations that are ascribable to the different inputs, including this random input.